Steve and Adam for the invitation to participate in this workshop, and also for laying on some good Scottish weather. Let's begin the standard. Let's talk about left-orderability and toroidal three manifold for the three manifolds. So this is joint work with Steve and Ying who Steve. Okay. So let me begin by reminding people of the airspace conjecture, which is just the context for this work. So the airspace conjecture, which I guess was formulated by Boyer, Liam Watson, and myself, and then Hash. It says that for prime, let's say so for a prime, closed orientable, three manifolds, and the following are equivalents. Okay, three properties that are conjectured to be equivalents. So okay. Okay. The first is that the M is not an L space in the sense of Hilbert fair homology. And secondly, is that the fundamental group of M is left-orderable and non-trivial. And the third thing is a filiation property that M admits a co-orientable filiation. So let me not say too much about it. But, so this is a codimension 2. Sorry, codimension 1 filiation, which is thought. Every three manifold has a codimension 1 filiation, but thought is the key point. Well, co-orientable, everything. And so let's abbreviate these to. We'll just say that M is NLS. It's not an L space. I'm going to abbreviate this to M is LN, and we're going to abbreviate this to say that M is CTF. Okay. So that's the. I'm going to focus on. Well, okay, I'm going to talk about these in a little bit, but I'm basically going to focus on the left-orderability part. But yeah, so this is let's say a background conjecture. But it's still open in general. It's known for some classes of three manifolds. One implication that is known is that CTF applies NLS. So this is the result of Hosvath and Sabo. But all other implications are also open in general. All right. And so let me just say that if the first homology of M is infinite, then all these three properties hold. And so we sort of will assume that that H1M is finite. In other words, M is a rational homology sphere. Okay. Okay, and so I'm going to talk specifically about toroidal three manifolds, and so let me remind you of that. So a three manifold M, is toroidal if it contains an incompressible torus. So if there exists an incompressible torus T in M, and like I said, we might as well assume that the first homology of M is finite. So that means that this torus will separate M, and so therefore M is going to be the union of two pieces. Dealing along the boundary, so T is a boundary of X1, is a boundary of X2, and X1 and X2 have the rational homology of a solid torus, the rational homology solid tori. So X1, X2, rational homology solid tori. Okay. So that's the setting, and so for these manifolds, for example, you can take X1 and X2 to be exteriors of knots, and X3, for example, non-trivial knots. move them together, you'll get a toroidal manifold. Basically, we would like conditions under which we know whether or not this manifold M has one of these three properties, NLS, MO, CPM. So, actually, I can actually, okay, so here we are. So here's it. So the question would be, when is M such an M, such a toroidal manifold? When does this property start? Where star is NLS, O, or CTF? And so that's a general problem one wants to consider, and of course one wants to show that the answer is the same, for all three values of star, right? But now in the Hilbert flow world, in the Hilbert flow situation, well, this one's fixed. Okay. Okay. So if M is if they're asking the question about where is it to turn around with non space, this was answered. This is answered fairly recently by Hansen and Rasmussen, Jake Rasmussen, and Watson. And let me not sort of specifically say what the answer is, but let me state it in terms of a formulation which again is actually sort of due to Stephen Adam in terms of, so let's put this way. X is a rational homology solid torus, and it's got incompressible boundary, so it's not, so it's irreducible, irreducible, and not S1 cross S2. So this is going to be the general setting that we're going to be looking at. We're going to do two such things together on the boundary and ask when does the resulting closed manifold have one of these three properties. And so the field of Hansen and Rasmussen Watson can be expressed in the following in the following way. There's a set. Okay, so there's a set of slopes. Okay, so I use this Sx to denote the set of slopes on the boundary of X. So the boundary of X is this torus, this incompressible torus. A slope is just an embedded essential simple closed curve, right? Usually they're parameterized by the rationals if you choose a basis and so on and so on. And so the point is that you can express the Hansen-Rasmussen-Watson theorem in the following way. There's a set of slopes on the boundary of X, which depends on X. So this D stands for detected. So these are the NLS detected slopes. Okay, that's it. Such that, so what's the property? Well, such that if you bring together two such things like X1, X2, if you give the term rational homology solid tori, you get this closely now. So X1 union along the boundary, X2. This is not an L space. If and only if you look at the set of NLS detected slopes on X1, and then you can also look at the set of NLS detected slopes on X2, and these are sets of slopes on this common incompressible torus, and so you just want this to be non-empty. So you want some slope on this incompressible torus along which the two things are glued, so that it's NLS detected X1, NLS detected X2. So let me not exactly define what this set is, but it can be defined, and it has this property. So if you can figure out what for a given X or a given X1 and X2, if you can figure out what this set of slopes looks like, then you can answer the question about what happens when you glue two things together. So that's the kind of paradigm. Now in the other so again, there are similar well, for the other two properties, LO and CPF, the fundamental group being left-orderable, and the manifold having a coordinate federation. Again, there are similar definitions. Yeah, there are analogous definitions. Let me put it that way. You can define a set of slopes. Again, in the boundary of any rational homology set of torus, with the property that I think one implication is it holds. So in other words, right, we get this. Let me just say that in the case of LO, this definition. I mean, the definition of this is due to Stephen Adam. And as I said, it was their work on the S-mass conjecture for graph manifolds which led to this sort of general kind of formulation in terms of these sort of detected slopes. So again, one refers to these as the LO detected slopes and the CTF detected slopes and so on and so on. And I guess in the CTF case, so this was, I guess we did this. So there's a kind of, I mean, there is a kind of uniform sort of, in which one can try to at least study the question. And of course, if the L-space conjecture is true, then first of all, this should be reversible, as in the NLS case, and all three sets of detected slopes should be the same, right? This, for a given rational homology set of torus, the set of NLS detected slopes should be the same as the LO, which should be the same as the CDF. But of course, we don't know that in general, and so it's of interest to. Well, okay, so this is the general sort of framework, and so I should say one thing that. Oh, sorry. I thought. I have a question. In the box that explains, is the intersected slopes, the slope that are in the intersection on the right, do they play a role in how you do X1 and X2 together on the left? Oh, absolutely. Yeah. So you bring these things together, and you have to. Okay, it says that the resulting manifold is not an L space if and only if there's some slope on X1 that's not detected. Yes, and there's some slope here, and they're identified. You see. Mm-hmm. That's that's right. So yeah, that's right. I mean, because the boundary of X1 and the boundary of X2 are glued together, then we can think of them as that's right. So we look at the intersection, yeah. Yeah, so that's exactly the game. I mean, we need to understand what these sets are, and then if you know enough about them, then you can say, well, if you glue these things together in this particular way, then it'll have the property or won't have the property, or whatever, right?
Well, when you say glue that on the boundary.
What?
This light.
Well, sorry, I was supposed. So you take two rational homology set of tori, X1 and X2.
Oh, okay.
So they have boundary a torus, and you choose some homomorphism from the boundary of X1 to the boundary of X2, and you use that to glue them together.
Yeah, that's clear to me. But
okay, sorry.
But then the slopes shouldn't match up to.
Well, I mean,
a linear transformation of one slope should be equal to one slope in the other.
I mean, it's almost psychological, right? But I mean, once you want to say, okay, glue it together somehow, right? And now you ask, okay, I've chosen some way to glue, and so now I can identify the boundary of X1 is this torus, right? But let's just say it's the boundary of X2, right? So there's this, and so I can ask. For any slope on that common torus, I can ask, is it in the set NLS X1, or is it? And if there's some slope that's in both, then.
Okay, no, I was just thinking in terms of numbers.
Yeah, of course. I mean, ultimately, one does get into that. Exactly. I mean, you get into the specific, but this is a very general sort of picture I'm trying to paint. But yeah, I'll say a little bit more in more detail, of course, later. One thing I will say, it's tempting to think. So here's a kind of remark that if you take some slope, if you take any slope alpha in the boundary of one of these things. And if you do Dane filling, right? So this is Dane filling. If you Dane fill this manifold with torus boundary along slope, obviously you attach a solid torus, so that the median of the solid torus is identified with the slope. If this has, this property star, then indeed that does imply that alpha. The alpha does belong to it is star detected, but the converse is not true. So in fact, this is very important. So I haven't said what this said is, but it's not. It's not this. Okay. And in the early days of it, way back 5-10 years ago, when people first think about these, there was a real confusion about this. And this was one of the points. But anyway, so whatever it is, it's not just you do a Dane filling and you see whether the resulting thing has property, the property star. If it does, then you're good. If it doesn't, you might still be good. So that's anyway. Okay. So like I said, what we want to do then, we want to find conditions. So we want to find conditions, on X or whatever on alpha, so you can know that a given slope is in one of these sets. The detected slope, star detected. So the real conditions under which, for a given X, you're given this X, this rational homology solid torus, and you're given under which, what would you say about this? Okay, so let me state a theorem that sort of says something about this. There are more general theorems, but let me just state one result. So here, we've got this rational homology solid torus. So there's a distinguished slope on the boundary, namely the rational longitude. So this is the rational longitude of X. So in other words, this it generates the kernel of the map on first homology with rational coefficients, from the boundary to H1 of X. So the kernel of that is a one-dimensional subspace, and there's this slope that generates that. And in fact, this guy is always in fact, if you do a Dane filling along that longitude, so you attach a solid torus, so that this rational longitude, is identified with the boundary of a manifold disk, then the first homology of that resulting manifold would be infinite. See, because this guy's rational null homologous, and so you've got a closed manifold with infinite first homology. And I intimated right at the beginning that all such manifolds, they satisfy all three conditions, and so certainly then, lambda is going to be, it's going to be in there, for all three values. Okay, but that's just one slope. That's not so interesting. Not so useful. Here's that it gives you more slopes that are in there, and then. Is there a clock in here?
You talk for 20 minutes.
Let me see. Okay, good. All right. Yeah, so let me just state the theorem, and I'll mention some applications, and then I'll maybe say a few words about the proof in the LO case, which is what I was advertising to talk to me about. So let's just see what that is. Okay, so here's a theorem. So let me call it. Okay, well I'll call it theorem one. There's only one theorem. Okay, so this is a joint work with Stephen Ying. Okay, so X is a rational homology solid torus. The usual thing. is irreducible and not S1 plus S2. And let's assume that the rational longitude is actually integrally non-homologous. Okay, that's an extra assumption. And let's pick a slope alpha in the boundary of X. There's an intersection number 1 with lambda. So, you know, we typically refer to that as the distance between. Okay, so for example, I mean, an example to keep in mind here would be, this is an example already, that the complement of the exterior of a non-trivial knot in S3, and alpha is the meridian, right? Because, you know, the exterior of a knot, well, it's an integral homology solid torus, right? And the longitude is, well, it's certainly therefore it satisfies this. And you know, the meridian is intersection number 1 with the longitude. So that's an example. Okay, but what's the theorem? The theorem is that alpha is always in this. It's always NLS detected. And the second, what about RL? Well, if X is an integral homology solid torus, for example, you know, a not exterior, it would be then in fact alpha is LA detected. And again, if X is a bundle, if X5 is over the circle, then in fact alpha is it's CTF detected. Okay. So I mean, there are no general statements that one can make, but this is so one statement which already gives some, you know, it gives some useful information about certain toroidal manifolds and whether or not they satisfy these properties. So let me just mention some applications of this, and then I'll say sort of the proof of the third part. So sorry, the second part. So I think I mentioned in the abstract that, well, I said, well, you know, some of the applications, you know, they give you evidence for the truth of the airspace community. So that's one aspect of this. There are certain situations where you know that, you know, a certain manifold, you know, has one of these properties, then if you can show that, well, it also has another of the 3 properties, then you kind of so one application is to integral homology sphere. So if you take an integral homology sphere, it's a conjecture of Orthoth and Sabo that wherever L spaces, if you've got a prime integral homology sphere, wherever no L spaces are S3 and the Poincare homology sphere within a finite fundamental group, and therefore they're L spaces. And there aren't any other homology spheres known to be L spaces. And so that's an Orthoth and Sabo, because I conjecture those are the ones. In particular, if you're toroidal, right, then you're certainly not one of those, and so you should not be an L space. And that was proved by F. actually, that if N is a toroidal integral homology sphere, well, that implies that M is not an L space.
Strange conjecture. They find another content will need to be added to the list.
Well, yeah, well, the point is, you see, if you're an integral homology sphere, then you're a Hilbert homology. Well, it's just sort of one-dimensional. It's really small, you know. And so, as long as you're a Hilbert, if you're an L space, then your Hilbert homology has to be really, you know, would have to be really small, right? I mean, that's, and the only examples where it happens just seem to be just the kind of really rather trivial ones. So, I mean, I think, you know, philosophically, there is some, I mean, yeah, yeah. But don't worry, there have been any other kind of examples. I mean, yeah, they know what they're doing. But yeah, even the problem with homology sphere is just an accident, right? I mean, it happens to have finite fundamental group, and you know, it happens to be a homology sphere, and it happens to be not simply connected, but it's just a weird little thing, you know. It's like 2 among the primes. Anyway,
Spherical geometry.
I'm sorry.
It has spherical geometry and then most like, I don't know, land spaces.
Yeah, the same is an space, yes. But it's the only one which is for among those, that's only I'm talking about.
Like, it's not like. It makes sense.
You got an argument one has over a beer, right? I mean, there's no answer. All right. Okay, but now I was going to say that actually, Hanson and Rasmussen and Watson generalized this to say that if M is, well, if this are M toroidal, and the first homology of M has order less equal to 4, well, then we found M is MLS. And so one thing that we can prove using the second part of this is that this is also true for LO with it. The implies M is LO. So you know, again, that's some of this. And by the way, this what's this 4 doing there? Well, the point is that there exists toroidal with, I mean, it's the best possible. In other words, you know, with that's why Z5 such that M is an L space. It's an L space and not LO. I mean, it's an L space, and therefore, if it's not CTF, right? If it's an L space and it's not L. So 4 is the best you can do. Okay. Clearly, that's so what I'm saying is that here are some things that were known, you know, in the Hayek flow setting, and now we're proving the analog, you know, in the orderability setting. So again, that's some evidence perhaps that things are work. So that's one application. Let me mention again a very similar application where the Hayek flow result was already known, and now we can prove the corresponding orderability result. And this was the this is the theorem about L space knots. So okay, so I mentioned this here. So now we're going to say if K, well, if K is a knot, then S3, you know, R is a rational number. This is you know, R brain surgery on K. Okay, and so that means that's any non-trivial brain surgery, you see. And so there's a theorem. So there's a theorem of Krasavich. So an L space knot is a knot that has a non-trivial brain surgery with an L space. And Krasavich showed that L space knots are prime. So one way to say that is that if K is composite, then if you do then any non-trivial brain surgery is not an L space. So, okay, so that's the thing. And I've been using yeah, essentially, I've been using essentially the second one. I say so we can show the if K is composite, it's LO for all of it. So again, this is a right. So that's another application of this. Because by the way, if you're taking the present now, any non-trivial brain surgery is always going to be toroidal. I mean, that's the point really. So let me mention well, essentially perhaps one more application, maybe a couple, and I'll say something about some of the proofs. Okay, so another application is to cyclic branch covers of links. So if you have an oriented link L in the 3-sphere, so it's got exterior, let me just call it XL. And let me do the segments of NL to be the angle cyclic branch cover of L. So you have to orient L to really know what that means, right? Because you have to know what, yeah.
Sorry, I'm not sure if I remember correctly, but under certain circumstances, if you want to do the time feeding of satellite node, for example, then you will get an airspace energy.
So, but you can get airspaces by soldier on satellite nodes.
But it would be less space, the resulting minimal.
No, I don't think so. I think it'd be kind of be a connected sum of a land space and an airspace.
Okay.
I mean, it works out, but yeah, but what's that's another question though. I mean, right? I know a composite node is a satellite. Is that what you're thinking? A composite node is a satellite node.
I think there's some result about cyclic activity on satellite node.
Yes, there definitely results about results about cyclic danger on satellite nodes. Yeah, yeah. But there are also results about airspace surgeries on satellite nodes. That's right. That's right. Oh, yeah. In fact, there are many results now. Yes, that's right. That's right. But in general, yeah, this is I mean, so this is one field, right, where the NLS result was known, and now we know the LA result. In general, the NLS technology is more advanced, you know. So more is known about if you do get a satellite now, where do you get out in L space? I mean, more is known about that than the other question, although they're catching up a little bit, you know. So yeah. Okay, so let me mention this thing about it was a sort of, I guess, the sort of conjecture that grew out of work that I did with Ty Woodman a long time ago. Again, we looked at the airspace conjecture for cyclic branch covers of knots, and you know, and cyclic branch covers of links, and gradually, I guess this conjecture sort of arose out of it. If you got a prime link, and if the exterior is toroidal, see, so it has an incompressible torus that's not just boundary parallel, then that should imply that all the cyclic branch covers, you know, are well, I mean, they should satisfy all these three conditions, you know, for all greater equal to 2. So so we can't prove, but we can't prove the following. So let me just say what we can prove here. So again, if L is a prime satellite link, then the following, well, then you get that, yeah. So let me state this, and I'll make a couple of them. Well, first of all, this is true. It's ARS. These cyclic branch covers are never L spaces. They're also left-orderable. They're left-orderable fundamental group. And in the CTF case, we need to assume that the companion knot of the satellite, you know, is fibered. So sigma L is CTF. You know, for all n greater than 2, if the companion knot is fibered. So let me say something like this. So if you have a toroidal link, that just means that in the exterior of the link there's some incompressible torus that's not boundary parallel. Okay. Now a satellite link is actually a special case of that, where you see, where if you look at that torus in the exterior of the link, that's called a T. You can ask in S3, well, sorry, in S3, that solid torus, sorry, that torus, it bounds a solid torus, right? Has to bound a solid torus somewhere, right? And the other component, maybe it bounds 2 solid tori. So if it bounds 2 solid tori, with a Hilbert sphere, then that means that because it's essential in the link exterior, that means that each solid torus must contain part of the link, right? But in the satellite case, the satellite situation is where this torus, in S3, it bounds a solid torus on one side, and the link is entirely contained in that solid torus. And so that means the other part is the exterior of a non-trivial knot. So that's a satellite link. And a toroidal knot is a satellite knot. Okay, the difference is a case where you have more than one component of your link. So satellite links are a special case of toroidal links, and And for them, we can pretty much answer. We can pretty much answer this question. Anyway, and then there are slightly more things you can say, but let's leave it at that. But let me just start write this down. But we mentioned that a lot of this work, certainly Michael, was inspired by a question that Alison Moore asked a long time ago. She, and usually the guys asks the student question, but in the other way around, she asked me. She said, "Wait a minute, she noticed that if you have an L-space knot, there's some knot that has circular L-space, then the double branch cover seems to be essentially never an L-space. Of course, that's not quite true because the trefoil is an L-space knot, and its double branch cover is an L-space. So there are a few counterexamples among small torus knots. But apart from those, she wondered, well, if you have a knot that is an L-space surgery, is if you have a branch cover of an L-space, it seemed like it's apart from these torus knots, maybe not. And it turns out that a lot is known now. It's known that if you have an L-space knot, then none of the cyclic branch covers are, let's say it's not one of these torus knots, one of these very small torus knots, then none of the cyclic branch covers are L-space, except possibly when n is 2. This is exactly the case that she asked about. And that's sort of still open. But if you replace not being an L-space by LO, which according to the L-space conjecture, they should be equivalent, then we can answer we can answer her question. In other words, if you have any L-space knot, all the cyclic branch covers are always they also left group, unless they are one of these very small torus knots, where like the trefoil, where the first 5 cyclic branch covers have finite fundamental group. But apart from those, it's fine. So it's kind of interesting that her question is still not answered, but every generalization sort of is answered. She knew exactly which one to ask, kind of interesting. Anyway, I'm just mentioning, and that's how it follows from, that essentially follows from, okay. You need to, this handles the satellite case, and then to handle the hyperbolic case, you use some other work that Stephen and I have done more recently, but anyway, I won't say more about that. Okay, so let's see. Okay, I better say something about some of the proofs. So let me say something about the proof of the second part of the theorem about LO, right? So remember we have this rational it's X, but we have this it's this rational longitude, and then we have a slope alpha that is intersection number 1 with that guy, and we claim that if X actually X is an interval torus, then that slope alpha, is LO detected, and that statement lies behind many of the applications I mentioned. So let me say something. Okay. So first, I mentioned that the notion of LO detection, in other words, this set, D sub LOX, that is the correct definition of that is given by Stephen Adam. And let me not give the definition, but let me say that, as you know, the orderability has this sort of dynamical sort of characterization, in terms of actions of the group on the real line. In fact, a find of Boyer, Wilson, and Reist, right, says that, if you've got a 3 manifold, prime 3 manifold, let's say, then its fundamental group is left-orderability if it has a non-trivial homomorphism. The fundamental group to the group of homomorphisms of the real line, orientation perturbing. So if it only acts non-trivially on the real line. And so it turns out there actually is, there is a dynamical, it's an analogous sort of dynamical characterization of the set of detected slopes and the boundary of rational ones. Let me not do it, but can ask Steve or Adam. But in particular, let me give a dynamical statement that is sufficient to show that a slope is detected. So here's a proposition. So again, we've got this rational homology solid torus, and it's irreducible, and it's not S1 plus S2. And we've got some slope alpha on the boundary, right? There's some slope. And we've got a homomorphism, we've got a representation from I1 of X to 100 plus R. The orientation preserving cores of the line. Such that, okay, so here's the condition. Suppose the knowledge of the boundary, so we've got this Z plus Z, right? Which comes from the boundary. So we've got the Z plus Z acting. If this has no fixed point, so there's no point that's fixed under all the elements of the triple subgroup, no fixed point in R, but okay, no fixed point. Let me move this way. So, but if alpha doesn't have a fixed point, where alpha has a fixed point, then alpha is in fact ordered. So you can think of this as a definition, if you like. I mean, just temporarily of what it is. So it's a dynamical kind of. And this is what is going to be used in the. Okay, so let me. Given that, then let me just sketch very quickly. Maybe 10 minutes or something.
Sorry, is the characterization or just?
It's just one implication, but the other implication, I mean, you have to modify it a little bit, but it's analogous. Right. I mean, this is too strong, but it's certainly implied that you're okay. Yeah.
What does that mean? The row of I1 boundary has no global fixed point?
Yeah, exactly. There's no point that's fixed by the whole of that.
Oh, okay.
That Z plus Z, right, yeah. So it doesn't have a fixed point, but this particular element does have a fixed point, then that element is order detecting. So I think, as I say, first pass, I mean, you can think of that as maybe just sort of almost perhaps you think of it as the definition of being order detecting. It's not quite. But this is the form in which we're going to use it because right. So let's let me say so let's now sketch. Let me sketch the proof of theorem 1, part 2. So again, here now we've got an integral homology solid torus, right? And we've got this slope alpha, which is distance 1 from the well, it's not that longitude, but now of course it's an integral longitude, okay. And we want to show that this guy is well, it satisfies this condition. So we're going to get this action on the legal spectrum. But we start with a filiation on X given by Gabai. So let's choose some minimizing surface in X, probably embedded that generates the relative H2. So this is a minimizing generator of H2 XL boundary. But of course, the boundary of F, you see, is going to be this. It's going to be this longitude, right? Okay. And so Gabai tells us that there's a co-interval foliation on this in which this is a leaf, F is a leaf. So X has a foliation F. This compact surface is a leaf. Okay, so that's kind of the starting point. Well, and okay, now we're going to double this. So we just take let's double this. We take X and then we take minus X and we do them together and we take this foliation and so just double everything along the boundary. And we're now going to apply this universal circle construction. It goes back to first, and of course it was also done by Canavary and Dunfield. So let me say the Thurston, Canavary, Dunfield. So we just follow them gives us. Well, I mean, the point is that, you can choose a random metric such as the induced metric, and all the leaves, is hyperbolic. And so every leaf, there's going to be some circle of infinity, and you can kind of, all these circles of infinity are images of a universal circle. And you can get an action of the whole fundamental group on this universal circle. And so that's what we do. Okay, so yes, they give us a let's give it a universal circle, which is a homomorphism. Let's say rho sub W from the fundamental group of this double gadget term homologue plus S1. This is this universal circle. And so now, well, just if you just restrict to restrict to 1/2, so we get a representation of our. The thing with the guy is the structure of this models you saw of torus there. And now, of course, as you all know, I mean, the game is to lift this, but so let me just remind you that we've got this exact sequence. So we call this homeo Z. So this is a subgroup of homeo plus R. This is just okay. Let me. So we've got the orientation between homeo to the circle. The universal cover is the homoverse of the line that commute with these integer translations. So these are just the sort of Z. So this is isomorphic to Z. There's a central extension where this is just the Z translations. And we want to apply this theory. So we want to lift this representation. Of course, we can do that just because we're assuming that I need to go. So there's an error class, which is the obstruction to lifting this, but this is 0 by assumption. And so therefore you can lift. So rho lifts to rho 2 and pi 1 of x to, well, to this subgroup of the orientation for setting polymorphism of the real line. Okay. And here's the point. I don't also don't have time to so much, but the key point here is so one can show a couple of things. First of all, we can show that if you look at this, if I have the original representation with the homologue plus S1, and look at this curve lambda, which is the boundary of this complex surface equilumber, this has a unique fixed point. And that's okay. So that has a unique fixed point. Let's go back 0 on the circle, and therefore the height of the boundary, you see, fixes x naught, because commutes everything in here commutes with lambda, and so x there will also be a fixed point for. So we're going to get this condition that the this is down in the representation into the circle, and then the second thing is that when you lift to rotate you see, because this is a lift of the circle, there's a translation number, and so the translation number of this lifted thing here, it is non-zero. So those are the two sort of key properties that we're proving. Let me say why. Let me just say why one expects of that to be true. See, we have this. Remember, this universal circle. It comes from looking at all these circles that are created with these hyperbolic rings. Well, F. If I look at F, that one part of F. It doubles, to give some compact surface S, and you have a hyperbolic structure on that, right? And so that means that you see the action on the circle here is really just given by this PSL2R representation of pi 1 of S, and under that, this curve lambda, it's a hyperbolic element, and then isometry of the hyperbolic plane, and so it's going to have this unique fixed point. And also, again, it's known that when you lift, then it's going to have non-zero translation number. In fact, the translation number is going to be twice the genus of the surface F minus 1. And so the trouble is, that's not the circle you're acting on. It's this universal circle, right? But and so yeah, there's a bit of fussing that, well, I mean, there's a lot of fussing that believes that that suggests that maybe this should be true. So the actual universal circle has a quotient, which is the circle I was talking about, the circle of infinity of this particular leaf, but it's not quite anyway. But okay, and so but one clarify. So I want you to show that, then they're basically done. So let me just finish off here. You see, so now we yeah. Let me finish the proof. Yeah. So because X is a limit of homology, so it's the first one is Z, and it's generated by alpha. We got this curve alpha that was due to the longitude, and so it's the generator of Z. And so, you know, we could define a homomorphism P from pi1 of X to, well, we factor through H1 of X, and then we map to this central group of translations by sending alpha. See, we want alpha to have a fixed point. See, then we lift. The fundamental group is not going to have a greater fixed point because the translation number, the translation number of the lift of the image of lambda is non-zero. Okay, so we would like alpha to fix a point, and then we can apply this thing and say alpha's in the set element. And of course, it may not be, but the point is, we just adjust that. We look at the translation number. Well, let's see. I don't like it. Yeah, so we just do a trivial adjustment with a homomorphism that sends alpha to this, and now we can define a new representation rotate a prime from pi1 of X. ZR by just you know, we just any element in gamma is we change it by this translation from gamma, and so zero till gamma, and so now we're done because the way we've chosen this now the translation number of alpha under this new representation obviously is zero. That's why we chose it. So that means that you know rho alpha has a fixed point. On the other hand, because this homomorphism, you know, factors through H1, so it's not going to affect lambda, and so the translation number of the new guy, it's still going to be, that's still going to be non-zero, and so therefore by the proposition we're done. So that's a very quick sketch of the argument here, but yeah, it means that so look at this formulation, look at the universal circle action, and then lifting it. Okay, I'll quit there.
Are there any questions? Yeah. So I guess the result is by cyclic coverings are coming from the fact that this is well behaved under pattern covers.
Well, yeah, that's I mean, if you have a satellite link, you have this link in a solid torus, and then you have a non-exterior. And when you get a cyclic cover, you take a cyclic branch cover of the solid torus branch over the link. Okay, that's some junk, and then you've got, well, again, you know, you might have assumed that all the tori are separating, you know, so now the non-exterior is going to lift, there's going to be some cyclic cover of the non-exterior, and you've got a bunch of copies kind of glued on. And so you have to have a version of the theorem when you glue things together that has several tori, but I mean, there's a sort of multi-slope version, but I mean, once you have the version for two, then you can prove a generator. So that's the picture, and so what we do, yeah, it's the key point is it's the this branch covering of the solid torus over the length, you really don't know what it is, but what you do know is that if you just look at the lifts of the rational longitude, you know, they're all going to be, they're good, you know, and they're identified with the lifts of the meridian on the null exterior. And we found that the meridian, you see, well, they're detected by the theorem, right? I mean, you see, right, their distance one from the rational longitude of these cyclic covers. The cyclic cover of the null exterior would be a rational homology solid torus, otherwise we're done. And the longitude is integrally non-homologous because you've got this separate surface. And we're looking at this, quote, the meridian upstairs, which intersects that once, you see. And that's identified with the rational longitude. But the other stuff. Does that make some sense?
I mean, I was thinking that you could some like definitions of as well in the subgroups of this construction. Well, I guess I was sort of concerned that your theory is for homologies of the tori, and when you might, I was wondering about the homology that might help.
Well, but like I said, you, oh, yeah, sorry, I misspoke a little bit. I mean, it's right, it's because, yeah. It's because downstairs it's an integral homology solid torus, that's right. And then you just look at the, you look at the subgroup, yeah. Yeah, no, you're right, I didn't misspeak, that's right. I mean, that's exactly what you do, yeah.
Any other questions? No? Okay, well, let's thank Karen again.